So in this lecture on fluids, I wanted to talk about the continuity equation. And we're going to use the continuity equation to try and figure out exactly how fast a fluid is going to be moving through a pipe, let's say, but if the pipe is changing shape. So we're going to consider basically a case of, let's say I have this pipe where the pipe narrows from an area of A1 down to an area of A2. Now, if the fluid is moving at some velocity V1, what's going to be the velocity that the fluid's going to be moving when it gets down into the narrow section? And to do this, what we're going to do is we're going to consider a volume of fluid like so, which has a thickness x1 and a mass m1. And so we're going to make three assumptions about this. So these three assumptions are that the first one, which we're already using, the fluid is incompressible. So basically, we can't take a fluid of a certain volume and crush it into a smaller volume. And the second one is that it's a steady flow. Or basically, there's no turbulence. So the fluid is going to flow steady through there, and it's not going to mix. It's not going to mix around, which we mean by the turbulence. It's just going to move from the left to the right without swirling around. And the last assumption is that it easily starts to flow, or it's what you would call non-viscous. In that it doesn't take an extra amount of pressure to get going, it'll just keep moving on its own. So the idea then is if we have this volume of fluid right here, that this volume of fluid is going to become this volume of fluid down here. So it has a mass m2, and now it has a length of delta x2, like so. And so we just follow these assumptions, which basically if it's incompressible, it easily flows. So that means the mass 1 is going to be equal to the mass 2, which means that's the density times the volume. And since the densities are the same, basically what our incompressibility assumption says is that the volume of the first section is going to be equal to the volume of the second section. Okay. Now, the difference you have is that in this case, you have an area A1 times a length delta x1, which is equal to a different area, a smaller one, A2, times a length delta x2. So basically, the area shrinks. The area is larger in the first section of volume, but it's narrower, and then it shrinks down to a smaller area, which means it stretches out the length of it. Okay. So what we'd like to look at now is the velocities. The velocity of that first volume is how fast it can move, or basically it can move a change in distance, delta x1, in a certain amount of time, delta t. And the velocity of the second section is delta x2 divided by delta t. And so now we can solve for those. So delta x1 is volume 1 times delta t. Delta x2 is volume 2 times the change in the time. If we plug that back into our equation, we have a1 times v1 delta t is equal to a2 v2 times delta t. So we're measuring basically the same time span, the same amount of time it takes this volume up here to move. So this volume to move at delta x1 and this volume to move a distance delta x2. And what you get is that's done in the same amount of time, delta t. So delta t's cancel, and we're left with what I call the continuity equation, which is the area 1 times the velocity 1 is equal to the area 2 times the velocity 2. Or we could now find the velocity of the narrow section of pipe as the area 1 divided by area 2 times the initial velocity 1 in the larger section of the pipe. Now, if in our case here, A1 is greater than A2, that means my fraction A1 over A2 is bigger than 1, which means my velocity 2 is going to be bigger than my velocity 1. So a fluid flowing through a pipe, a large section of pipe that gets narrowed to a smaller section, is going to speed up, which hopefully you've kind of recognized in your experiences in the past, because if you've ever done anything like water your lawn or water something with a garden hose, if you put your thumb over top of the garden hose, you basically narrowed the area with which the water can escape the hose, then the water is going to speed up. And it's usually going to then be shot a much further distance, because if something's moving faster, it can travel a larger distance in the same amount of time. So, so now we have a very simple equation, which is based on just the area of the pipe and the velocity of the pipe, and the velocity of the fluid inside the pipe. If I want to slow a fluid down, then I would go back to my equation and I would look at this ratio right here and say I would open up the pipe. So opening up the pipe, making it larger, would then slow down any kind of fluid. So now what I can do is I can look at, say, a new quantity called the volume flow rate, and they call it in the book Q, which is basically how the volume changes with respect to time. So if the volume with respect to time, the units are meters cubed, seconds. So meters cubed per second. And if I go back and look at my definition of the volume, it was the area times the length. And so Q I could write as area divided by the length divided by the time, and delta x over delta t is the velocity. So my volume flow rate, Q, I can write as the area times the velocity. So now what I can do is I can write my continuity equation as either A1 V1 is equal to A2 V2, or I can write it as the volume flow rate 1 has to be equal to the volume flow rate 2. If I was to rewrite this, so volume flow rate 2 minus volume flow rate 1 is equal to 0. So in the end, now we have basically a conservation law that volume flow rate Q is conserved. It's a conserved quantity, which means that every place inside the pipe the volume flow rate is the same. It's the same volume flow rate in the larger area. It's the same volume flow rate in the narrower neck of the pipe. And so, yeah, what we're left with is this conservation. Now, what does change is the area, the cross-sectional area of the pipe, which then forces the velocity of the fluid to either speed up or slow down when I make changes to the area.